First I'd like to start off with a question. If you leave an object out in direct sunlight and you want it cool even below the surrounding temperature, surrounding area's temperature, would something like that happen if you leave an object directly in the sun? Could you get it to cool below the ambient air temperature? So that actually does happen, and it's the phenomenon that I studied in my thesis project. So it's a study of selective emittance of nanoparticle coatings for passive daytime radiative cooling. The problem with traditional cooling methods, such as air conditioning, is that you need energy input for the technology to function, and also it produces heat and pollution as well. To address this, PDRC, or passive daytime radiative cooling, is proposed as an emerging technology which allows surfaces to cool below the ambient air temperature. That means the ambient air temperature is the air temperature of a medium which is not under the stable air temperature of surroundings, and under PDRC it will cool below that temperature even under direct sunlight. So if you leave an object out in the sun, it will still cool if it has that coating on top of it. So currently PDRC is implemented as nanoparticle or nanomaterial coatings on the surface which you have to cool. So something like this. Here has a bunch of cylinders which they make on top of the surface to cool, and it is found to be successful at cooling the object. However, there is not a lot of theoretical study of the fundamental properties of materials which allows for something like this to happen. And that is what I addressed in my research project. The 8 to 13 micrometer range of the electromagnetic spectrum is very useful here, because radiation in that wavelength would exit the Earth's atmosphere without being absorbed again. So if an object emits a lot of radiation within that region, 8 to 13 micrometers, it will not warm the immediate surroundings, and it will also not be absorbed by the atmosphere. So it's what we want to do, right? We want an object to cool down also without warming the surroundings. Now, if you use an AC, it will cool the inside of a building, but will emit a lot of energy outside. Here, it will not warm the surroundings and will also cool efficiently. So if we take a radiative cooler, that means it cools by emitting radiation, it will absorb energy from absorb radiation from the surroundings, also radiation from the sun directly, and also warm due to conduction. Right? Maybe you make a coating and you spray it on your material. That material would have thermal energy. The coating would absorb that energy and emit it as electromagnetic radiation. So in this study, I focused mainly on the solar radiation and also the radiation that the object itself emits. The other two are not very, they are negligible compared to the ones that I mentioned. So first let's discuss the Kirchhoff's law of radiation. This is extremely important in my study. It states that a black body in thermal equilibrium both emits and absorbs all radiation in the same intensity. So here in my study, we approximate a real object, a real material as a perfect black body. So we want to maximize the emission power. So because of that black body approximation, we try to maximize the absorption, because it's the same, it's a black body. And I quantify this emission or absorption using what is called the absorption cross section. So it's defined as the power of radiation that it absorbs to the intensity of the incoming radiation. So this is a flow chart of the arguments that I made in my study to achieve my goal. So the goal is to maximize the absorption cross-section of an object, of a material. And to do that, so this is what we exactly need. To do that, we can go through a couple of steps which we make as an informed approximation. So the first is that solar reflectivity and transparency. So if we go back to this diagram here, this is the solar spectrum. It has a high absorption and emittance. So the sun emits a lot of radiation towards Earth in a wavelength spectrum less than 3 micrometers, less than about 2 micrometers. The area that we need is the 8 to 13 range. So because radiation does not come from this region, it will not warm our material. So we would think now if the material maximizes absorption, we want to maximize emission. To do that, we maximize the absorption. So if we maximize absorption, won't it get heated up by the sun? That is a valid question. But it won't happen here because the sun's radiation is outside of the radiation region that we optimize our material for. So it will not warm up due to solar radiation. It will take all its thermal energy of the material and will emit it as radiation. So under the solar reflectivity and transparency approximation, we by maximizing net cooling power, what we do is we maximize radiative power. And so power is directly related to the cross-section quantity as I defined above. We can say we maximize the emission cross-section there. So maximizing the radiative power is the same as maximizing the emission cross-section. And under that Black-Body approximation, it's the same as maximizing absorption cross-section. So that is what we actually need to do in this field. So what has actually happened is I have shifted the problem of obtaining optimal emission, that is what we need to get. I've shifted that problem to obtaining optimal absorption. So all my subsequent calculations and arguments are about maximizing absorption. What actually happens is it also maximizes emission. But absorption is what this approach and these software that are used, and they all work with absorption. So maximizing the absorption is useful. So to summarize my objectives of this study, it's to find the material, take any material and find properties of that material which maximize this absorption cross-section, or to find what changes to the material you can make to maximize, to change the maximum P. So it's actually, so ultimately it's equivalent to maximizing the cooling efficiency. And I modeled my particles in terms I modeled my materials in terms of the particle size and also refractive index. So I made a lot of assumptions that the material is only particles and only considering a single type of particle and a single surrounding medium. And the cross-section values are calculated using what is called mean theory and the discrete type of approximation. We will get to that later. So mean theory is actually the solution to Maxwell's equations of electromagnetism, and it for a sphere. So it describes how electromagnetic waves scatters around a sphere, a perfect sphere. In this study, I modeled particles as single spheres. So using this approach, reduces computational problems for a very simple case. So when electromagnetic waves are scattered around a particle, the intensity distribution is something like this. So this is a 3D figure. You get high intensities you get the intensity distributed in a shape like this. So changing the size of the particle and the refractive index of the particle would change the shape of these lobes. So when I experimented with different particle sizes, what actually happens was different intensities were calculated for the particles, and I obtained cross sections based on that. So the software I used was called Python. It takes these parameters and generates the output as a cross section. The discrete dipole approximation had to be used because mean theory is only valid for perfect spheres. The discrete dipole approximation is the approximation of an object, a continuous real object, as a bunch of discretized subvolumes, which is called dipoles. So it's not here. The dipoles are the plus charge and minus charge. It's a cubical volume which has a net dipole moment to it. So it's like it's as if one side has charge and the other plus charge and the other side has a minus charge. It works. So in such a case, there's a net dipole moment. So here we think of the object as a bunch of cubical volumes with a net dipole moment through it. And these dipole moments are useful because the electric field and the dipole moment and the refractive index information of the material is used to calculate these cross sections. So this is a summary of what actually happens inside the calculations. I did not have to work with these myself. These were numerically implemented in the softwares that I use. So that alpha is the polarizability. You can see it depends on epsilon j and I. So epsilons are refractive indices. The material is specified by the refractive index that we give to the software. Then the electric field at any point inside the volume is calculated using the incident electric field. This happens as if we are sending light from one direction towards our object and the light gets scattered around. So that incident radiation intensity electric field is used, and also the polarization is calculated from the electric field. So at the end it solves this equation and finds the E electric fields and the polarization. So this is the cross-section value that I mentioned before. These are all calculated inside the software. I did not have to work with them directly, but it's useful to understand the relationships between these quantities to understand what we are working with. So the electric field information is useful here, also with the polarization to calculate the extinction cross-section and the absorption cross-section. The absorption cross-section is the quantity which I try to maximize. So I simply modeled a material as a single particle at first. With the single particle, I was able to use P theory for my calculations. Then, when I needed to simulate multiple particles, I had to use the discrete dipole approximation. So that shape particle distribution I generated on Python using a code that I created. It's a matter of generating points in a given region that you specify, and that information was used in my scattering calculation software. So also the material's permittivity was permittivity information is specified here. A real material does not have a single permittivity. The permittivity changes with the incident wavelength. So we have to give all that information, how all of it varies, and software calculates the cross section based on this given information, including particle sizes. So my approach simulates nanoparticles as spheres. Actually, particles aren't exactly spheres, but it's a valid approximation. It's often done in research in this field of nanoparticles in general, and also the overall material as a collection of spheres arranged in a layer. Also, random arrangement of spheres is also possible. So, under my approximations, I gave the particle sizes. I actually changed the particle sizes, refractive index of the material, refractive index of the surrounding medium. Just mainly those three factors, and obtained maxima in the absorption cross section. This is exactly what I needed to find. So this plots like these are somewhat similar to this. So in the 8 to 13 range, emittance or absorbance is maximized. It has a really high value and a low value outside of it. And my calculations are for single sphere, so you get a wide distribution, but there is a maximum somewhere, and I found that increasing the size of the particle would shift the peak to the right, and decreasing it would shift it to the left. As you see here, and then I could also make the real and the imaginary components of the refractive index to obtain different conditions. So I found that the cross section is maximized at an optimal refractive index of this value, and also there is a very complicated relationship between the refractive index and the cross section, which I am not able to here. But the point is that all these factors can be accounted for when studying this, and it's useful to study that way. So I did this. So my previous calculations were for single spheres using knee theory. This is for single spheres. These are for single spheres and arrays of spheres using discrete dipole approximation. So they were found to give pretty much the same results for single spheres. And when simulating an array of spheres, the data was once again similar to that of a single sphere, but I proposed that using simulating an entire array of particles would better describe the real material, right? Because having a single sphere not surrounded by anything is not a good approximation for real material. Other particles around that material would influence the way light gets scattered around that particle. So solving this problem for an array of spheres is recommended in my proposal. So I also studied a particular material called cellulose. It has some research interest here in Sri Lanka. There's a group working on this passive beta mediated cooling, and they are interested in using cellulose byproducts of other processes and as a PHYSOC material. And I did the same analysis for this material and found that it is indeed suitable for PHYSOC applications. So, to summarize my results, I found that the peak can be shifted to the right by increasing the particle size and also increasing the refractive index's imaginary component. Also, there is a maximum, there is an optimal refractive index which maximizes the cross section as we needed. And cellulose is found to be a good material for PHYSOC applications. So, at the end of my analysis, I concluded that we can indeed change the size of the particle and the refractive index of the material and the surrounding medium to vary the peak in the absorption cross section. And these results can be used as a guideline when synthesizing real materials. So you can observe these trends that I found here. One can observe these trends and figure out what changes to their already existing material they need to make in order to improve its cooling efficiency, or get an idea for what sort of new materials they can synthesize. So that is, these are actually the most valuable insights gained from my study here, and this study can also be extended to study more complicated structures. I only studied single spheres and arrays of spheres. So there are way more nanostructures, nanowires, nanotubes. Those also can be investigated. Yes. So I'd like to thank everyone who helped me with my research project. Dr. Alessandro of our department was my main supervisor. It was also co-supervised by Dr. Luca from the University of California. And they have a research group on passive data and radiative cooling, which helped me with the information and opinions while carrying out my research. So, and I would also like to thank you all for your attention. And I'm open to any of your questions.